AC, the current chapter, which is a shortcut for alternating current. So what is alternating current? This should be our first question, right? So far, we have learned about DC. DC represents direct current. And what is the meaning of this direct current? It means the current always flows in a one direction in the circuit. It doesn't change its direction, with the time in the circuit. That is called as a direct current. And to drive any DC circuit, we use a battery. We use a battery. But whereas alternating current is opposite to direct current, what it represents or what it means is the current or the direction of the current changes with the time. Then it is called as an alternating current. Example of DC would be something like this. With respect to time, this is how the current would be. Whereas in case of AC, the current would be somewhat like this. Need not be always like this. It can be even like this, where the amplitude of the current keeps on repeating after a particular amount of time or after a fixed interval of time. That is called as an alternating current, because we use alternating current in many applications. Generally, rather than compared to DC, we use AC more in the world, isn't it? The main supply that we have in the home is of 220 volts and 50 hertz AC. Whereas in case of US, they have 110 volt, 60 hertz AC, right? So unlike in DC, the voltage of the voltage source keeps on changing. And so accordingly, the magnitude of the current also keeps on changing. So we can say that here, this current I is a function of time t over here as well, right? So in general, the current that we see in our households is of the form I naught sin of omega t plus 1, or the voltage that we see is V naught sin of omega t plus. So we can say that here basically current and voltage both are sinusoidal functions, isn't it? So a sine function looks somewhat like this. Let's say if we take about I, the amplitude is I naught, and this would be minus I naught. Okay. And it continues with time like this. Now, the time period between two consecutive maximums of amplitude, this time is called as time period of the signal T. Let's say the angular frequency with which it is oscillating is omega. Then we can say that T is equal to 2 pi by omega, which represents this part. So omega into T represents the angle theta, right? So that's why it is basically I of T is I naught sin of theta plus alpha. V of T is V naught sin of theta plus alpha. In case of DC, we represent the battery or the voltage source to be like this. This is a DC source. In case of an AC, we represent it. This is called as an AC source. Whereas the rest of the passive elements like a resistor, capacitor, and an inductor, all these three elements have the same symbol, whether it is a DC circuit or an AC circuit. The only difference is how the voltage source is going. The voltage source is represented by this symbol, right? Now, since in case of AC, the current is not constant at all times, since it is changing with time, we have different parameters for current, or we represent the same current, instantaneous current, in different ways for a better understanding of it. Okay? So the two important ways of representing this current is average current and RMS current. We all know what is average, right? It is basically nothing but the total sum by, for the total amount of time. But since here we have a function in terms of as a function of time t, we will try to see how to find this average as well as RMS. Starting with, let's say, the general equation of current I of t as I naught sin of omega t. Then the average current, I average, is given by integral I dt by integral dt. We can find few interesting facts in this. One is, let's take a sine wave of this sort, where this is I as a function of time t and this is time t. Integral I dt. Now we can do this integration from 0 to capital T. Then what happens to this? So basically numerator is nothing but the area enclosed by this curve and with the x-axis. I can say that if this area is plus a, this area would be minus a, net area would be 0. So I average over one full time period is always 0. Whereas I average over a half the time period from 0 to t by t. It is integral 0 to t by t. I dt by integral dt from 0 to t, which is integral 0 to t by t. I is nothing but I naught sin of omega t dt, but denominator becomes 2. It is 2 I naught by t into integration of sin is minus cos omega t by omega. Limits of integration are from 0 to t. So, which is nothing but omega t is 2 pi. So 2 I naught by 2 pi is I naught by pi with a negative sign. Cos of omega t by 2 is minus 1. Minus cos 0 is 1. Which is nothing 2 I naught by pi. So we can say that the average current is nothing but 2 by I times of the peak current. But what should we take? Should we consider the average current to be 0 over a one full cycle? Or should I consider the average current to be I peak by pi over a half cycle? We will be considering this because we can never say that current never flew, or the current or the energy transfer did not happen from the voltage source to the passive elements like resistor, capacitor, or inductor. Isn't it? So I can always say that the I average, or the, remember, whenever I say that I average, it is always between 0 to t by 2, that is for the half cycle. Okay. So this is important formula which you have to remember, that is I average is 2 by pi times of I2. The next parameter in current is IRMS. IRMS, also called as a root mean square. The name itself suggests it is a root of mean of the squares. And how do we calculate this? It is integral I square dt by integral dt. This is mean of the squares, but we need to have a, since we are already squaring I, no current goes in the negative direction. All the current, or all the values of current I square will be always positive. So it becomes I naught square sine square omega t dt from 0 to t divided by 0 to 2 dt whole power half. is I naught square by t into sine square omega t can be written as 1 minus cos 2 omega t by 2 whole power half. That is I naught square by 2t into. There is a dt here. In the numerator, it becomes t minus sine 2 omega t by 2 omega whole power half, where limits of integration are from 0 to capital T. Simplifying it further, we have I naught square by 2t into t minus sine 2 omega capital T by 2 omega minus substituting 0. It is 0 minus 0 whole power half, which is nothing but I naught square by 2t into t minus 0 minus 0 whole power half. T and t gets cancelled. I RMS is pi. This is again an important formula which has to be remembered because we are going to use this directly in the questions. That is, I RMS is always given by peak value or the amplitude divided by root. Now we will see what will be the different components in the voltage function or current function in an AC circuit. Let's take voltage function. V of t is equal to V naught sine of omega t plus. Here, V of t is an instantaneous voltage. V naught represents the amplitude of the voltage or the maximum voltage. We have here either sine function or cosine function. Omega is called as angular frequency and phi is called as initial phase. This omega t plus phi is together called as the phase of the voltage, because omega is always measured with respect to the reference voltage, or omega t is always measured with respect to the reference value, that is x-axis. Right? Now this omega is angular frequency, which can also be written as 2 pi by t or 2 pi f. Anything will work. Okay. Now we'll see what happens when we connect different elements in an AC circuit. Starting with, we'll see what happens when we connect just a resistor in the circuit. Okay. So how the circuit is going to be? We have a resistor and an AC generator. Let's call it as, let's say its voltage is V naught sine of omega t. Its resistance is R. Before we get into this, we have to understand how this resistor will behave when a voltage is applied. Can I say the voltage across the resistor is nothing but the source voltage Vs? Because the resistor and the voltage source are in parallel connection. So VR is nothing but V naught sine of omega t. Or VR can also be written as current through it into R is equal to V naught sine of omega t. Therefore, current as a function of time t is given by V naught by R times of sine of omega t. We can see that current is some amplitude into sine of omega t. Whereas voltage across a resistor is equal to some amplitude into sine of omega t. We can see that here both current and voltage are always in phase. Always in phase means if current is high, even the voltage will be high. If current is low, even the voltage will be low. If current is zero, even the voltage is zero. This is how it's called as being in phase. Yes, both the functions will rise to their maximum at the same time, come to zero at the same time, take negative positions at the same time, and again come to zero also at the same time. This is called as in sync, right?